Hello everyone, so in this specific video I'm going to talk about ResNext, which is a Resnet but now modified with a next dimension, and in the dimension that we are dealing with here is the cardinality dimension. So basically the ResNext architecture is the Resnet architecture, but now with the residual block having an additional dimension known as the cardinality dimension. So that is what we want to look at in the core architecture, in the core of the ResNext architecture when we're implementing it. So let us implement the classes that we'll be using in the implementation of the ResNext architecture. And then after doing that, let us see the base residual block of the ResNext architecture. So when we look at the base residual block of the ResNext, we essentially see that the residual block for the Resnet architecture, we notice that it has a 1x1 convolution, then followed by a 3x3 convolution, then again a 1x1 convolution, of which we saw that the last layer of a residual block essentially had 4 times the number of filter as the previous layers. So in this case, the cardinality dimension, basically what it does is to split the input into groupings, of which those groupings will be passed through convolutions, and then later on the outputs of the residual blocks will now be concatenated. So in this case we see that, for instance, we see that basically we will be implementing the architecture C that we see here below, what we see in our diagram. So basically what we'll be doing is the residual block first will pass through a 1x1 of 128 filters. That is from 256 filters, then the output is 128. So then the 128 filters now will be passed through, will be split into 32. That is cardinality. The cardinality now is 32, which is 32 groupings. Now these 32 groupings will be passed through convolution layers that have been stacked into groupings of 32, such that now each will now be four filters each, and then later on the outputs of the stacked convolution layers will be concatenated, and then they'll be passed through a last convolution layer of 1x1, and then the output now will be summed with the skip connection, after which we'll pass it through a ReLU operation, and then we take it out of the residual block of the ResNext. So ResNext essentially modified the residual block such that it had groupings of conv2 layers which were stacked depth-wise in order to introduce the cardinality dimension. So in this case, essentially we see that when originally the Resnet architecture would work on 128 filters of conv2D, kernel size 3x3, here we would have 32 stacked convolution layers, each having 4 filters, and also each of kernel size 3x3. So here we see the implementation of the group convolution, where we see that essentially what we will do is take the output channels that we require. That's, in this case, the output channels will be 128. Then we divide by the cardinality, which is 32, so that we get the number of filters of the groupings to be 4. Then we would loop over the groups, which is 32. So we will build stacked convolution layers, 32 of them, each of filters size 4x4. Kernel size will remain 3x3. Then the stride will be passed depending on the required stride in the residual block of a given stage of the ResNext architecture. So after building the depth-wise stacking of the convolution layers, what we do, we divide the inputs in according to the cardinality dimensions. So in this case, this one is from 0 to 4. This one will be from 0. Since we know that group in will be input channels, which is 128 divided by 32. This is 4. Then this one will be also 4. Since the input is 128, the input to the groupings is 128, the output is 128. So it would be 4. Group in num will be 4, group out num will be 4. So in this case, grouping num will be from 0 to 4. That's now 0, 1, 2, 3. Then we go from 4 to 8. Then all the way up to here we see that we have now 32. We have 4. So we'll go all the way up to when the groups are now 32. So in that scenario, now we'll be splitting the inputs so that they can be passed through through each convolution stacked depth-wise. Then the output will now be concatenated. As we'll see here, the groupings will be concatenated before it's returned back to the calling variable. So that's how the group convolution 2D is. Now in this case, this class has implemented this one. So this one is the architecture of the group convolution which was implemented, and this is the residual block for the ResNext architecture that would implement, considering that it was the simplest and also it trained faster than the others. Actually, it was simpler to implement than the others. So that's the core reason why this one was the architecture C was chosen over the others. So after that, now we'll implement the next part, which is the residual block, where we pass it through a normal convolution, then through a group convolution, then back to normal convolution, and then we sum the input and the skip connection. So after implementing that one, which is the group convolution here, we would implement the bottleneck. We have a normal convolution. Of course, after the normal convolution, there's the batch normalization and the rel operation, which will implement in the call function. Then after that, now we have the group convolution. We also have the batch normalization, and then all the way to the rel operation. And then the third one is now the normal convolution, the batch normalization, and the rel operation. And then after getting that one, we also get the output to the skip connection which will be convolution, batch normalization, and then we had the two. So this is the bottleneck architecture, which we see here. So here we see that the layer that we see is basically a convolution, but there's also, after the convolution, there's always a batch normalization and a ReLU. Also after the group convolution, there's a batch normalization and the ReLU. Lastly, in this convolution, there's also a batch normalization and the ReLU. Then for the skip connection, it's only convolution and batch normalization. So that's what has been implemented here. We see that we call the normal convolution. We saw that it has kernel size 1 by 1, then the filters were 256. The input filters were 256. So if it were PyTorch, we would have specified the input and the output filters. But now for TensorFlow, the conv2d class essentially takes the output filters. So this one will basically be 128, which is also the same to the output of the group convolution, again 128. And then we see that for the last convolution of the residual block of the ResNext architecture, we have 256, which is 128 by 2. So we see the output here is 256. Then after we've seen that one, we also see that the group convolution is kernel size 3 by 3, which is contrast to the first convolution and the last convolution, which each respectively have kernel size 1 by 1. And then after that we implement the call function, which essentially creates a graph for the flow of the inputs in the residual block of our ResNext architecture. So this is how we implement it. And then now we want to implement now the ResNext architecture, considering that we've now dealt with the residual block of the ResNext, which was the main concern as of now. So we see that the ResNext, the only difference was the cardinality dimension, as we saw earlier, which we said is the dimension which was added on to the ResNet in order to make it the ResNext architecture. We see that as opposed to the ResNet, where we see that the last layer has 4 times the last layer in the residual block, that is, has 4 times the number of filters as the first convolution and the second convolution layer in the ResNet block. We see that for the ResNext, the last layer has 2 times the number of filters, and then the middle convolution layer has a cardinality of 32, which means that the 128 filters will be shared such that each convolution stacked depthwise will now be having 4 filters as outputs. Then they'll be concatenated to form a complete a single output from the group convolutions, and then they'll now be passed on to the last convolution layer of the residual block of the ResNext architecture. So now let us finalize by seeing the flow. So the input is convolution. So the paper essentially says the input is convolution. Then of course there's the after convolution there's batch normalization, and there's also a max pooling. So when we're implementing the input, we implement the batch normalization and the max pooling before we start to loop through the bottlenecks that we see here. So essentially we started with the implementing the group convolution, and now we implemented the residual block. Now the next part is to implement the repeating nature of the residual blocks, which I see here. So we implement the output filters that we want. Then after implementing the output filters, we implement the strides, the groupings, and the repeating number. So in this case, the repeating number will be, for ResNext 50 would be 3, then 4, then 6, then 3. So here we pass a single number 3, then it will be there will be implementation of this bottleneck, which is as a result of repeating ResNext bottleneck. So it will build the repeating ResNext bottleneck, and then it will return it to the calling variable. So here we implement here. So So in this case, I'll use num class as 10, but for the training of the ImageNet, you can use 1000. So essentially, here we want the number of lists. Essentially, we know that the lists of the values that make up the ResNet, or rather in this case the ResNext, is 4, such that is 3 4 6 3, or maybe 3 4 23 3, something like that. So whenever it's not equal to 4, then raise an error and cancel the operation. So here we see that as I had said earlier, the input is a convolution filter 64. Then after that we have a batch normalization and then a max pooling before we start the operation of the ResNext bottlenecks. So we see that in the first scenario, whenever we pass, for instance, if we'll pass ResNext 50, we'll have 3 4 6 3. So in the first ResNext block that will be built, we'll have 3 as the value here, and we know that essentially only the first stage of the repeating bottlenecks has a stride of 1. For the subsequent stages, the stride will be 2 2 2, and this is one of the cases that we also saw with Resnet. So we see that ResNext is so much similar to Resnet, and the only differing factor here is the cardinality dimension, which has really been emphasized in this architecture. So we see that in the first stage we have 3, then after that it will be 4, then it will be 6, and then lastly it will be 3, as seen from our architecture diagram here. 3 4 6 3. The cardinality is constant at 32, and then the output filters will now be 128, 256, 512, and 1024. So as we see here, it's 128, 256, 512, and 1024. And after finishing the repeating ResNext bottlenecks, we go to the global average pooling 2D, and then we pass lastly through a layer known as the dense layer with the units 100, 1000. Now for me I've used 10, but if you want to use 1000 for maybe training or the ImageNet dataset, it will be okay. And then the activation function is softmax. So here now when we create the ResNext, now when we want to essentially create a function that instantiates the ResNext 50, that's it. And then for the ResNext 101, which we said 3 4 23 and 3, that's it. So when we now create a dummy random uniform rank 4 tensor, we can pass it through so that we can build our model, after which we can get to see the number of parameters in each model, in this case the ResNext 50 and the ResNext 101. So as it runs, basically this is a ResNext explained in its finest. We see that it's really easy to understand, considering that there's not much difference between this one and Resnet apart from the cardinality dimension. And furthermore, this cardinality dimension also ensured that there was low parameters on the case of the ResNext. So we see that essentially maybe you can confirm on the part of the low parameters. I'm not sure, but I think that's also one of the major reasons why ResNext really did well, because with a lower number of parameters, it could outperform a Resnet of at least same number of parameters, as it had a high accuracy, considering when taking into account a smaller model with a lower number of parameters. So you see that here for the ResNext 50 we have about 37.7 million parameters, and then for the ResNext 101 we have 74.9 million parameters. So as simple as we had started this one, now we have ended this video, and we see that essentially it does not take a rocket scientist to understand the architecture of ResNext. And so thank you for watching. Let's meet in the next video.